Guys, there's not that much sun outside, which is fine. So I'm going to taught myself self-taught acupunctures. I got acupuncture saved my life last year, and I ended up getting more energy in the fall than I have. Let me figure out. Okay. So that's thyroid point. Alright, so let's do. I'm just doing the points suggested for thyroid. So I think I have the kidney points. I need to be the shaman. The heaven gates. Guys, I've only done a little acupuncture and I'm already starting to feel better. Alright guys, so there's my little acupuncture for today. I'm gonna start doing it every day for 30 minutes. They say all our organs are in our ear. So right now I've just gotten the thyroid points, so I'm ready to start my cellular training. Alright guys, so this is how I am in my solar training. I'm on 3rd module.
We'll be using some of the same conversions as we did in the previous lesson. These square meters to square feet, Celsius to Fahrenheit, and then Fahrenheit back to Celsius, square inches to square feet, square millimeters to square meters, and watts per square foot to watts per square meter, vice versa. So take a few minutes and review these conversions and then go on to the lesson. Some terms we'll be using in this lesson. ASHRAE, this is the American Society of Heating, Refrigerating, and Air Conditioning Engineers. Incident angle, this is the difference in angle between the degrees of the direction of the PV array is facing and the position of the sun. NOC, normal operating conditions, we looked at this in the previous lesson. And NOCT, the normal operating cell temperature, we looked at this in the previous lesson as well. The INOCT is actually the installed normal operating cell temperature. So the NOCT is what we expect to see based on a standard test from the module manufacturer, but the INOCT is the actual temperature difference based on the location that we installed the PV array. So it may be actually hotter or cooler depending on the parameters of installation. Standard test condition, we covered this in the previous lesson as well, 25 degrees C and 1,000 watts per square meter. Temperature coefficient. This is an effect on voltage and current that is consistent with incremental changes in temperature. So when we vary from that 25 degrees C, there is, depending on the particular module we're using, there is an incremental change in voltage and current for each degree C of change. Extreme annual dry bulb mean. This is the extreme highest and lowest mean temperature without humidity. And mean is very similar to average, except it points to a particular range in this temperature. Let's take a look at some module performance characteristics. Irradiation, the sunlight that strikes the PV cell. We have direct radiation, which occurs during the middle of the day on clear skies. Current is proportional to the level of radiance. It'll go up with higher radiance and drop with lower radiance. Voltage is pretty stable with all different radiances. However, with a lower radiance, around 100 watts per square meter or less, a lot of technologies will collapse at that point. Diffuse radiation. This is early morning, late afternoon, evening, and cloudy days where we have a lot of reflected light, and some cell technologies don't function well in this type of radiation, and others perform very well. So we try to look for a module that'll get into this range a little bit. So about 20% or less, typically it depends on the climatic conditions of the location, but no more than 20% of the daily energy is in this type of radiation. Temperature effects on PV cell voltage and current. Well, voltage is primarily affected by temperature changes. As the temperature goes up, the voltage drops, and as the temperature goes down, it'll increase. So when it deviates from standard test condition, we see this change. Current is only minutely affected, so we don't really pay too much attention to that as installers, designers. Performance variances between PV cells and modules. This does occur during the manufacturing process. It's hard to keep everything perfect, so we do have some cells that produce more than other ones. That doesn't mean that the ones that don't produce as much are bad. They're not. They just don't produce as much energy, and this variance can pull the whole module down. So we have a lot of products on the market that try to fix that problem. Light-induced degradation. This is UV radiation for one thing, and then natural decay of the doping materials in the PV cells. So this reduces voltage and current, but primarily current. Reflection of light occurs at the glass level. Most of the light that is not reflected is refracted in. So if we can defeat the reflection, then we have a really good solar glass. And most of the glass that we use these days has a little textured surface, so it prevents the reflection and gets that refraction into the PV cell. Irradiance has a large effect on current. We base our current on 1,000 watts per square meter from a standard test condition, and so when the level changes, it changes the current as well. So our example, we have a 200 watt module with a standard test condition rating of 5 amps, and it's exposed to 1,000 watts per square meter, then what we should read is 5 amps. If the irradiance is less, 800 watts per square meter, then it'll produce 4 amps. That's 80% of 5 amps, so it's pretty easy to make that calculation. Temperature is a little bit more complicated, but not much, and it has a large effect on voltage. So when the temperature changes from the standard test condition of 25 degrees, then it's going to affect the voltage by a certain percentage. If you don't know what the cell technology is, we assume that 0.5% per degree C is being gained or lost depending on whether the temperature goes up or down. Most of the new modules have an effect of about 0.35 to 0.4%. When the module temperature is above 25 degrees, the voltage will drop. So in this example, 45 degrees C temperature is 20 degrees hotter than standard test condition. So we have 20 degrees times 0.5%, that's a 10% drop in voltage. On the other side of the coin, if the module temperature is below 25 degrees, the voltage will rise. So if we have 5 degrees C, that's 20 degrees cooler than standard test condition. We have 20 degrees times 0.5%, and we get a 10% rise in voltage. This chart shows us the difference between various technologies. We have the monocrystalline on the right-hand side, older technology. You see that the temperature coefficient is higher. The newer technologies have been able to drop this temperature coefficient down, primarily because we are converting more energy into electrical energy and less is decaying to heat. As we move to the left, we see some of the thin film technologies that have lower temperature coefficients than the crystalline. When we take two technologies together, such as the one high-tech, second from the left, and we mix the crystalline with the thin film, then we get the benefit of the thin film and a lower temperature coefficient. So we see that benefit from that mix of two technologies. All module datasheets provide us with three temperature coefficients, one for VOC, one for Power Max, and one for ISC. We don't use the ISC, it's of no use to us, and the incremental change is very, very minute, so we just ignore it. The VOC is to calculate the coldest day voltage whenever the temperature is low, and the Power Max is to calculate the voltage loss and the power loss that occurs during the actual operation of the PV array. When you look for the extreme dry bulb mean temperature, you can go to the local weather station and ask them for that specifically. Say, I want the extreme annual dry bulb max and mean temperature, and they'll give it to you. Or you can go to the ASHRAE web site and download this table.
Cool.
I think we have a copy of this in your files. You can download it. It has all the major cities throughout the United States listed, and it has the max and mean temperatures as you see in this chart at the bottom part of the page. Calculating cell temperature. For the coldest day VOC, we're looking at the early morning when the sun first comes up. There's no irradiance on the PV array, so there's no current. We just have open circuit voltage, and the voltage is at its full potential. For the hottest day voltage, we're looking at direct sunlight on the PV array, and we don't know how hot it's going to be on our particular array, but we do know from the module datasheet that the NOCT is based on 800 watts per square meter with an ambient temperature of 20 degrees. So we can base our hottest day temperature on that and determine how low our voltage is going to go during the rise in temperature during the day. So we look at the data sheet on the next slide, and we see that the NOCT is 46 degrees. So that gives us a 26 degree increase in cell temperature over ambient. So if the ambient temperature is 37 degrees, then we know that the cell temperature will probably be at least 26 degrees hotter than that in direct sunlight. So that gives us a cell temperature of 63 degrees. The installed normal operating cell temperature may be higher or lower than the predicted NOCT. It depends on whether it's a ground-mounted system or if it's a roof-mounted system with very little airflow. One thing that takes a little time and familiarity is the different data sheets from module manufacturers. Take a look at all the modules that you plan on purchasing, look at their data sheets, find out where all this information is so that you're familiar with it. What we're looking at here is a Sun Module Plus. There's three different modules represented here, the 690, 695, and the 300. These all came through the same manufacturing facility, and they should be all the same, but they're not, so they break them into efficiency categories and sell them individually. Let's go to the right-hand side. We're looking at the 300 watt module, and of course it tells you that it's rated 300 watts. And then right below that we get the open circuit voltage, 40.1. That's the open circuit voltage at standard test condition. Then we get the max power voltage, 31.6. We're not doing anything with current right now, so we're just looking at the voltage adjustments for temperature. Next thing we want to do is take a look at the temperature coefficients and the NOCT. It says here the NOCT is 46 degrees C, and this is whenever the ambient temperature is at 20 degrees. That's always the case. Anytime you see NOCT, they're basing this on cell temperature when the ambient temperature is 20 degrees. The next thing is the temperature coefficient for open circuit voltage. It's 0.3% per degree C. And then right below that is the max power, TCP max power, and that's 0.41% per degree C. Our voltage formulas for calculating coldest day voltage and hottest day voltage. We have the coldest day voltage we're going to look at first. So what we're looking at is the absolute difference between standard test condition and the ASHRAE coldest day temperature. So we're looking at that dry bulb mean temperature. So if it's a negative number, we're looking at, minus whatever up to plus 25 degrees. What is that difference? We're not looking at a positive or negative number, just that difference. And we'll plug it into our formula. It's pretty simple. Take that degree difference times the temperature coefficient for VOC that we pulled off of our module data sheet. And that gives us the percentage change. We know that the voltage is going up, so we're multiplying that by VOC and then adding it to the VOC. Or we can do the simple thing that I've shown here, which is just add a 1 to that decimal, because your percentage will be represented by a decimal. If it's, let's say, 10%, then you're going to represent that with a 0.1, and then you'll add the 1 to it, the 1.1 times the VOC for standard test condition. Now you have your new voltage. For the hottest state calculation, we do something similar, but first we have to find the difference between cell temperature and ambient temperature, and we know that we have this given to us on the NOCT part of the data sheet in the module, so we're just going to assume that this is the case. So if we have an NOCT of 46 degrees on the module data sheet, we know that's 26 degrees greater than the ambient temperature. So if we have a new ambient temperature that's hotter than that, we simply add that 26 degrees to that new ambient temperature. And we have the cell temperature. And now we want to take the difference between the cell temperature and standard test condition. And then once we get our difference, just like we did in the first example, we just multiply that by our temperature coefficient, but this time we're using max power temperature coefficient. And that's the percentage change in voltage. It's dropping, so we're actually going to lose voltage in this case. And so what I usually do is, since we have a percentage, let's say it's 0.12, I'm going to put a 1 minus 0.12, so I'm going to have a fractional of 0.88. So 0.88 times whatever my VMP would be, will be the reduced voltage on the hottest day. Well, let's do an exercise so we have these formulas down. We have a location with a max temperature of 37 degrees C, minimum temperature of minus 11 degrees C. So for our coldest day voltage, we'll first find our difference between the standard test condition of 25 degrees and the ASHRAE minimum temperature. So we have minus 11, which is 36 degrees less than 25 degrees C. So that's our multiplier. We take from our data sheet the VOC temperature coefficient, which was 0.3%. That's represented as 0.003. We multiply that times the 36 degrees difference, and we end up with 10.8%, or 0.108. And I pulled that 1 in, so I have a 1.108 times the standard test condition voltage, which is 39.9, and that raises our voltage to 44.21. So now we know what the coldest day voltage for this module will be at this location. Now our hottest day voltage, we calculate very similarly. We have to find the cell temperature first. So we know that we have a 26...
Guys, I'm going to get through it.